All right, hey everybody, we're back. All right, give me a couple minutes just to set up and then we'll get started. Okay, all right, so let's go and get started. Let's see, right on 5:45 on the dot. All right, so we've in case you people on Zoom were wondering, we're all safe. We all survived the evacuation drill, so it's all good. All right, so how's everyone doing today? Doing good? Good. All right, so first before we start, I'm going to apologize a bit. I am feeling a bit sick. I took my cousins to an anime convention over the weekend. One of them is only 10 years old, and basically whenever I presented him with food, something, then he would just like and then like stew like all over the food. So I shared some of that with him. So I'm feeling a bit sick, so my voice might be a little bit nasally, and I might be kind of out of it a little bit, but hopefully I can get through this. Okay. So we have quite a busy day today. So we only have an hour compared to a normal lecture, but I did want to talk about the midterm exam a little bit. I know I sent that email out to everyone, but I did want to talk about it in class today in case you guys have questions on that. I also posted the final project. Now, the final project, you probably you guys are not going to be working on until after the Thanksgiving break or after the midterm exam. But I did want to introduce it a little bit today, just in case you wanted to talk to me about kind of what you're thinking about for the project. And then we need to finish our lecture notes on transient simulations. Okay. So quite a bit on the agenda, but hopefully we can get through all of it. Okay. All right. So before I begin, so if you have questions on the midterm, I would say just hold off for about 5 minutes. We're going to discuss it soon. But besides the midterm, are there any questions I can answer before we get started for today? Okay. All right. Good. So let's talk about the midterm exam. Okay, so hopefully everyone got my email, but the midterm exam is going to take place on Thursday, November 21st. So it's going to take place during the lecture time, so it'll be a 75-minute exam. Okay. In terms of content, you can expect it to be all on the direct stiffness stuff. So there's going to be no answers on the exam, nothing on meshing or the boundary conditions that we've kind of talked about before. Okay. So the two most important documents that kind of help you with study, well, first of all, the lecture notes and your own notes, those are going to be the most important. But to help you with your studying, I did post a study guide. So I believe I linked that in the email that I sent you guys today. So make sure you take a look at that. In terms of practice problems, you can expect the problems on the exam to be very similar to problem set 1. Which is what you guys are working on right now. That's due next Monday or Sunday. Okay. So those are your main 2 study tools, right? So I would definitely look at the study guide. If you look at the study guide, you should notice that the way I format it, the study guide is kind of formatted in a way where kind of each learning objective is kind of almost like a question. And so if you're able to answer all the questions on the study guide, if you're able to do all the problems in problem set 1, and when I say that you can do the problems, it's not that you're looking at the solution and then you're doing the problems alongside it. That's not really doing the problem. When I say that if you can do the problem, you should be able to do it without looking at the solutions until the very end. Okay, so if you can do that, then you're in great shape for the exam. Okay. Format of the exam. There's basically 2 sections to the exam. So the first section is going to test you on your conceptual understanding of the direct stiffness method. So those will be short answer questions. Okay. So short answer, to me, short answer is anywhere between 2 to 3 to 4 sentences long. Or sometimes if you draw, sometimes the question will ask you to draw a figure. Sometimes they'll ask you to maybe list something out, right? But basically that's kind of the idea. So this will be well, there'll be 4 questions. 4 of these types of questions. And this will be worth 40% of the points. Okay. The other section of the exam will be kind of problem-solving type questions. And for this class, there's only one type of problem that we've gone over, which are direct stiffness problems. Okay, so this will be worth 60% of the points. Okay. So added together, there's going to be worth 50%. Okay. So in these problems, what you're going to be expected to do, obviously, I'm not going to be asking you guys to plug in the matrices in MATLAB and solve the solutions. And so what I'm going to expect you guys to do is to carry out the problem all the way up until assigning the boundary conditions, right? And so, if you kind of, pay attention to the problems that we've been doing, there's a point where we get our global stiffness matrix and we assign the boundary condition to that. So we make the modifications to the matrix to assign the constraints and the loads, okay? That's the point where I'm going to be expecting you guys to stop. So I know some of you have graphing calculators that are able to solve linear systems. You won't have to do that. First of all, it takes a lot of time to plug in the numbers for these kinds of systems. I don't want you guys to waste, this exam is already going to be kind of long. So I don't want you guys to waste time kind of plugging in, numbers to a calculator and doing the matrix inverse. And so I just want you to take it up until you get the final stiffness system. So there will be two of these problems. And I think I can tell you this now. So one of the problems is going to be 1D, and the other problem is going to be 2D. So obviously the 2D problem is going to take you a little bit longer. So try to be a little bit strategic in terms of how you spend your time on the exam. Okay. Okay. And I think that's it. Oh, things that you could bring. Okay, so there should be kind of 3 items that you should bring to the exam. So one is your writing utensil. Okay. So pencil, pen, quill soaked in the blood of your enemies, whatever you use to write, whatever you're most comfortable with. Okay. 2 is a calculator. So it can be any calculator. That's only just gonna help speed up some of the multiplication and division that you have to do. So scientific calculator, graphing calculator, whatever is most comfortable. You can't use your phone, obviously, so anything besides your phone calculator is fine. All right, and the third one is people call it a cheat sheet, but it's basically just a sheet of notes. So you can write anything on your cheat sheet. So the size dimensions is just a regular 8.5 by 11 sheet of paper. And you can use both sides. You can type it, you can write it, whatever is kind of most comfortable to you, but you can only use kind of one sheet of notes. Okay. So one thing that people have done in the past is that they've taken my lecture notes and they basically made it really, really small and printed that really, really small in their cheat sheet. That's one strategy. It's not a particularly effective one. Because what I see a lot of times when people do that is that you spend more time kind of reading your cheat sheet than you do actually taking the exam. And again, this exam is I'm aware that it's long and I'm kind of trying not to make it too long. But just the nature of these problems and how big the matrices are, these problems are going to take you a bit of time, and you don't want to waste a lot of time kind of reading your cheat sheet. Right? What I always tell people is that creating your cheat sheet should be something that you actually do to help you study. Okay? So one 8.5 by 11 sheet of paper is not that much space, right? So if you think about all of the content that we've gone over for the past 5 weeks, right? Condensing all those past 5 weeks into just one sheet of paper is not easy, right? But by looking through your notes and kind of deciding and kind of filtering and condensing what you can into that sheet, you kind of naturally kind of study that content yourself, right? And so ideally, if you spend a lot of time in making a good cheat sheet, you're hardly going to use it on the exam because you already know it pretty well, right? So that's my hope. So I give you I guess what other instructors may consider to be a generous amount of cheat sheet on the exam. But I'm hoping that you're able to use that space to not try to cram as much stuff so that you read it during the exam, but that you can use it to actually write really good notes and then hardly use it on the exam. That's kind of the hope with that. Okay. Okay. So I think that's everything I wanted to say about the exam. Any questions on the exam? Okay. All right, so of course, if you have questions on the homework, if you have questions leading up to the exam, I have all my office hours. So you guys in this class, you'll be able to take advantage of all 5 office hours that I have remaining until the exam. So I have office hours tomorrow from 5:30 to 6:30, office hours on Thursday from 1 to 2, Monday from 5:30 to 6:30, next Wednesday, 5:30 to 6:30. And then for the absolute last minute questions before the exam, I have office hours on the exam day from 1 to 2. Okay, all right, so let me go ahead and let's talk about the final project. Let me share my screen here. That's not actually my password, don't try it. Okay, so if you go to the Canvas site, you'll see that the final project is activated. Now, again, I probably don't expect anyone to really start working on the final project in earnest until after Thanksgiving. But I at least wanted to give it to you guys now so that you can start thinking. So, because the big part of the final project is that you're going to be able to choose what you can work, what your subject for the final project is going to be. Okay? So we've kind of talked about this a little bit throughout the class, especially after the midterm project. But your final project is basically going to be a repeat of the midterm project with a few additional things that you have to do. But the big change is that you're going to be able to choose the subject yourself. Okay? That means you guys are going to be responsible for producing a CAD file for this project, and as well as coming up with the objectives and all that stuff. Okay. Okay, so basically the idea is to be able to, or to give you guys an opportunity to apply ANSYS to simulate a real world system of your choice. Okay. And so the purpose is to basically apply everything that you've learned in the class about ANSYS and finite element analysis to a problem of your own interest or your own need. Okay. So, a lot of you guys are seniors, you guys are taking senior design right now. So, probably the most popular choice for the final project here is to, apply it directly to your senior design project. Maybe do some analysis on the design that you have taken, or maybe design, consideration. Okay. If not, then you can choose, anything that you want. So you can choose a real life structural thermal component. I've seen people do historical components, and so I've seen people do maybe, a component of the Eiffel Tower. I think that's kind of a really interesting kind of type of project. Or maybe, a section of the Golden Gate Bridge, something like that. Okay. Or you could even design a whole new part. So if you're into kind of 3D printing yourself or your hobbyists, you can use the project to design something that, that you might be, you might be producing in the future. Okay. The idea is to kind of, let you guys choose and to choose something that will be useful to you and your. Okay, and so the only requirement that I have is that your problem be of appropriate scope. And so what that means basically is that the problem should be challenging enough so that you can kind of showcase everything that you learned. Okay, so I don't want you guys to do simulations on a steel cube. Okay, so it should be more complex than that, but it shouldn't be so complex that that you're not able to get a good simulation on. Okay, so there's kind of a sweet range there where which is appropriate for this class, appropriate for this project, but it's not too crazy. Okay, so generally what I recommend to people is that if you're not sure where your project's going to land, just definitely talk to me first. Send me an email, come to office hours, let me know what you're thinking, and then I can help you kind of workshop on your project and make sure that you're getting the most out of it. Okay, so that's the reason kind of why I'm kind of showing this to you early, so that if you are thinking about doing a specific kind of project, there's time for you to come, talk to me about it. Get feedback from me so that we're all kind of on the same page for that. Okay. Because I think what happened last year was that I waited until December to kind of showcase the final project, and then it was kind of a big rush at the end. So I wanted to make sure I give you guys enough time to think about it, and then to give you guys a chance to talk to me. Okay. Okay. Any questions so far on the on what's expected of the final project? Okay. Good. Okay, so let's go over the specific requirements. And so a lot of these will look similar to the midterm project, so I'm not going to dwell too much on them. Okay. So the first one is that you need to formulate an objective for your project. Okay. So just like the midterm project, you're not just simulating something just for the fun of it. So there should be some kind of goal or clear goal that you have in mind. Whether it be, you're trying to simulate the stresses to see if your part's going to break. Maybe you're trying to minimize the deflections of the part. Maybe you're computing factor of safety and you're trying to get that under a certain amount. There should be some kind of story or some kind of objective that comes along with your project that kind of drives and motivates your simulation. Okay. Hopefully for the final project, it's a little bit easier because, especially if you're basing it off your senior design project, your senior design project already has its objectives. So you can just repeat those objectives here. And try to work that into the goals of your finite element. Okay, background and significance. So since you are going to be coming up with your own project or your own geometry for this, you have to do a little bit of motivation too. And so, give me a little bit of background in terms of, what this type of part is typically used for, why is it interesting, what's the historical background of the development, what's the kind of technological question that it seeks to answer. So there should be a little bit more on the background significance. So it's not just a random handle, that you're simulating. There should be some background story. Okay. All right. Next section. So we'll get into this more after Thanksgiving. But one really important aspect of finite elements is to do what's called validation. Okay. So a lot of times when you're doing finite elements out in the professional world, it's not enough just to do a finite element simulation. You also have to, show that what you're getting is reliable. Okay. Because as powerful as a tool at finite element analysis is, there's also 1,000 ways to fuck it up too. And so one way that you can show that your results are good and they're reliable is to do what's called a validation experiment or validation calculation. Okay. And basically the idea with the validation is to do kind of a separate calculation ideally outside of ANSYS or outside of FEA to show that, you get a similar result, okay? So for instance, one very common way that people do this is that, they validate their simulation against some kind of real life experiment or real life observation, okay? And so if you can show that what you're simulating in ANSYS matches up what is in reality, with everything else being the same, with the same boundary conditions, then we know that your simulation is going to be reliable. Okay. So we'll talk about this more after Thanksgiving, and so there's kind of a lot of kind of strategy in terms of what you can do with validation. But this is a very important part of professional FEA, and so I wanted to make it part of the final. Okay, finite element modeling methodology. So again, this is pretty much identical to the midterm project. The only thing that's different is that you also must include a mesh convergence test as part of your methodology. Okay, so I am going to be looking for that, and for the midterm project, it wasn't a requirement, but for the final project, if you don't have the mesh convergence test, then I'm going to mark you down for that. So make sure that you include that. Okay. ANSYS results. Excuse me. So just like in the midterm project, you'll be required to show your ANSYS results, and so that's your deformation field, your equivalent stress field. Just like the midterm project, I am going to be requiring that you show me at least 3 configurations, and 2 of those configurations have to have some unique combination of boundary conditions. Okay. Okay. Then after your result, then I want you to compare your results together with your validation calculation. So again, we'll talk about that more after Thanksgiving. But ideally, what you get from your ANSYS simulation should match, or at least match in some way with your validation. Okay. And then you're going to have your conclusion as well. So the conclusion is usually pretty short, and just summarizes your result. Okay. All right. Any questions on the requirements for the project? Okay, deliverable. So there is only one deliverable. So that is a final report that summarizes your methodology and results. Okay, so I don't need your ANSYS. So just like the midterm project, I don't need your ANSYS files. I just need the final report. Okay, so your final deliverable should just be one PDF that you submit through Canvas. Okay. The due date for the final report is going to be Sunday, December 22nd. Okay. That is a hard deadline, so I cannot push that back under any circumstance because I do want to get all my grading done before Christmas. The school requires that I get all my grading done before Christmas, and so this gives me kind of just 3 days to 3 days to grade everything, not only for this class but for all my other classes as well. So Sunday is kind of the latest that I can push it back. So that's kind of a hard day. But hopefully that gives you enough time. From today, it's a little bit over a month, so it's about a month and 10 days. But that's as far as I can push it back. Okay. All right. So for the final report components, there is a template for this, just like the midterm project, and so I'll kind of leave that to the template. It's very similar. So the sections there are going to be very similar. The only difference is that there's some additional sections for the validation, which again we'll talk about after Thanksgiving. Okay. Okay. Teams. So for the most part, mostly everyone in the class is going to be doing an individual project. But that said, I am open to the idea of doing teams, but at most only 2 people per team. Okay. So the reason I open it up to this is because I know a lot of you guys are working kind of here are working on the same senior design project. And so I know for the same senior design project, there's only so many components of the project that you can simulate. And so if you are working on the same senior design project and you make a compelling case to me about why you should be able to work in teams, I am going to allow it. That said, the expectations for a team project are higher than an individual project. I am going to expect more loading configurations. I expect the methodology to be more detailed. So it's not a path to do half the work. Whether you do an individual project or a team project, it's going to be the same amount of work that you're going to do. But just sometimes it works out, for people that are working on the same senior design can do this, can kind of team up to do the finite element project as well. Okay. So if you plan to work in teams, I do want to approve it beforehand. So, if you do want to work with a partner, definitely let me know. And I'll kind of talk to you on kind of an individual basis in terms of, what's going to be expected for your project. Okay. sometimes it's not as straightforward as, adding a few more loading configurations or adding a few more to the methodology. Sometimes, for a certain project, there's ways that we can kind of, increase the work, but also making it more meaningful for you too. So if you do want to work in teams, definitely let me know. We definitely need to get my approval, but talk to me first, and we can talk about how to make it good. Okay. Okay, final remarks. And so, it's on the one hand, the final project is kind of the same rodeo as the midterm project. So you guys are kind of, you guys have already kind of done it once. But with that said, when you're doing your own geometry, a lot of new questions are going to come up. So, definitely don't hesitate to reach out. As everyone knows in the class, I'm very available through email. You can come to my office hours. You can talk to me after class. Don't hesitate to talk to me. Okay. Because I think, the worst thing that can happen is that we get to, December 19th, December 20th, 21st, and you start to have all these questions about the project, but, it's a little bit harder to get a hold of me during that time, just because, I'm doing grading, I'm trying to help other people. So, start early, talk to me early, and, I promise I'll do everything I can to get your questions answered. Okay. All right, any final questions on the project? Okay. All right, so start thinking about the project. Again, I don't expect anyone to really start working on it in earnest until after Thanksgiving. But it's good to start thinking about it now. Okay. All right, so let me go ahead and bring back the iPad here. Sorry, I'm starting to feel the sickness a bit more too, so I might be out of it a bit. Okay, but thankfully, there's not that much more that we have to talk about. Remember our next ANSYS activity is on Thursday. So it's been a while since we've done an ANSYS activity, but with everything going on, the midterm exam next week, I want you guys to focus on the midterm exam. So we are going to do the next activity on Thursday, but it's not going to be due until after Thanksgiving. Okay, so just kind of keep that in mind. Okay, but with that, we have to kind of finish up our introduction before the activity, because the activity on Thursday is going to be on dynamic simulations. Okay. So, so just to kind of refresh your memory of what we talked about last Thursday, everything that we've done in ANSYS and even in direct stiffness up to this point, have been static simulations. Cool. And so with static simulations, that of course, means a lot of things. But most importantly, what that means is that your simulation or your situation is not going to change with time. Okay? And so in fact, if you wanted to be more specific about this, our static simulations only had one type of variation, which was spatial variation. And so spatial variation means that our solutions only depended on the spatial variables. That's X, Y, and Z. when you have dynamic simulations add another dimension to the solution in terms of how it can change, okay? So with dynamic simulations, we're also going to be considering variations in time as well. Okay? The spatial variation is still going to be there, right? And so, we're still going to consider variations in X, Y, and Z, but we're adding kind of one way that you can think about it is we're adding an additional variable or an additional degree of freedom to our problem. Okay? So now we have solutions that depend on X, Y, Z, and time, T. Okay. So when you add a fourth dimension like this, it kind of changes how you have to do things, right? And so on the one hand, the characteristics of your solution are going to change, right? So that's kind of what we spent last Thursday talking about. Okay. And so the main thing that we talked about last Thursday was that, when you have dynamic simulations, there's an expectation that vibrations are going to occur. Okay. And so last Thursday we talked about, how those vibrations are characterized, what different parameters of the physical system are going to go into, the vibration characteristics. Okay. Oops. But the main thing that's going to change it, at least from our perspective, is how we obtain the solution as well. Okay, time is actually very interesting, and so having time as a variable, you have to kind of change the way you solve the problem a bit on the fundamental. Okay, and so in particular for finite elements, we have to enlist or we have to incorporate a kind of a family of algorithms known as time marching schemes. Okay. So, we could spend weeks talking about time marching schemes. And so there's a lot that are out there. Okay. We don't have weeks, we have about 28 minutes, right? So I'm going to do my best in the next 28 minutes to explain time marching schemes to you, at least kind of the essential things that you need to know, at least from a user's point of view. Okay. But just know that time marching schemes is a very, very rich theory. There's a lot of different kind of methods that are out there. And if you take a course in numerical methods, then you'll be able to learn more. All right, any questions on this so far? Okay, so let's go into how time marching schemes work. Okay. So the main reason why we need different schemes or different algorithms for time-dependent problems is that fundamentally time is different than space, okay? Time is what we call a causal variable. And what that means basically is that there's a strict sequence in which you need to solve things in time, right? And so you can't solve for things that are 10 time steps in the future until you solve for what's in the present. Okay. Right. So if you want to solve for things at t is equal to 1, you need to know everything at t is equal to 0 first. Okay, so there's a very strict order, a very strict sequence in which you need to solve things. Okay, that's not true for space. Okay, and so with space, right? If you want to solve for things on the other side of the planet, right? You don't need to know everything that's happening here, right? So space is not causal. So space, you can solve for things in different points of space, depending on just whatever's near it, right? So you don't need to know everything at a given point to solve things in space, but with time you do. And so the main method that we use to solve for time-dependent problems is called time marching. Okay. And so the idea with time marching is to solve for the solution in the next immediate time frame. Okay, so the idea is to use the solution in the present time to predict what's going to happen in the very next time. So the idea is like this. And so if we have u at n plus 1, okay? So u at n plus 1, this is the solution in the next time frame. This is going to be equal to f, where f is some function, okay? So f here is kind of an abstraction or a representation of the time marching scheme. So the solution in the next time frame is going to be a function of un, okay? Where un here, this is the solution in the current frame. So this is the current solution. M, K, C, etc. All of these properties here, these are the material and geometric properties of the subject itself. So I know this is a very abstract kind of a formula here. It's not even a formula, it's just kind of a representation. But the whole idea with time marching is that, in order to know what happens next, you have to know, everything about the current state. And how you factor in that current solution into your next prediction, that's kind of the science of the time marching schemes. All right, any questions on this? Okay. Another thing that you should notice from this is that, with time marching, we're solving for the solution kind of one frame at a time, right? In other words, you can imagine us kind of building up our solution kind of one, point in a timeline at a time. Okay. And so we have a timeline here. What we can say is that through time marching, we're going to get a solution at each point along this line. Okay. Okay. Let me go ahead and label the points on this timeline. Okay. So time zero here, that is our initial conditions. We're going to talk more about initial conditions in a second. Okay. So the initial conditions is usually something that you have to specify in terms of, what the solution looks like at the starting point. Okay. Then when you run the simulation, you're going to be predicting what the solution is going to look like at each successive time. Okay. And so, for instance, in order for you to predict what's happening at time point 1, you're going to use the solution at time point 0 to help you, determine it. Okay. Same thing for time step 2. So for time step 2, right? In order to predict what happens at time step 2, you need the solution from time step 1. Okay, so everything kind of solved sequentially one at a time. Okay. Okay. And remember, another thing that we talked about last time is that, when you solve a dynamic simulation, you're solving basically, hundreds or thousands of static simulations at a time. And so this is kind of a good representation. So every time you simulate a new time step, right? Okay. Each of these, you can think of it as kind of a separate static simulation. Now, I've only drawn 9 time points here, but in reality, when you do a dynamic simulation, you're probably doing this hundreds or thousands, if not, sometimes even tens of thousands, hundreds of thousands of times. Okay. So dynamic simulations, remember, are always going to be computationally more expensive than your static simulations. And I think this is no better illustration of this, by showing that, a dynamic simulation is basically hundreds or thousands of static simulations stacked one after another. Okay. Another analogy that we talked about on last Thursday was to kind of interpret a dynamic simulation as kind of like the frames of a video. Okay. And so each time point is going to represent the frame, a separate frame of our video. Okay. And they're all going to be played back to back. An important quantity and one parameter that you do have to specify in time marching is what's called the time step size, right? So the amount of time, amount of time that occurs in between the frames of your simulation, we often call that delta t. So delta t, the name for this parameter here is called the time step size. Okay. And what it represents, it represents the amount of time that passes in between the frames of your dynamic simulation. Okay. The time step size often is a user specified parameter, so you have to kind of specify that yourself. The closest comparison that I can think of for the time step size is that it's very similar to how you choose the mesh size. And so it's similar to the mesh size in that if you choose a smaller time step size, it's going to make your simulation more accurate, okay? But it's also going to make the simulation more expensive. So how do you choose the time step size? Well, it's kind of like the mesh size. So it's kind of something that you start to get a feel for, the more you do dynamic simulations. Unfortunately, there's no such thing as a time step convergence test, although maybe there should be. So it's not typical that people do, a convergence test with the time step size just because dynamic simulations are just so expensive. So usually, for the most part, people use a nominal step size that they kind of use for most problems. For instance, for the simulations that I do for my research, I usually use a time step size of about 1 millisecond. Okay. But it really depends on what you're trying to simulate. Okay. So for my case, for my application, I'm simulating blood flow in the human body. Okay? And so if you think about how quickly blood flow can change in the human body, things change about as quickly as your heart beats. Okay. So the frequency or the cadence of your heart beating kind of sets a natural kind of time scale for the simulation. Okay. Typically, on average, for most people, people kind of have a heartbeat of 60 beats per minute. So that's about 1 beat per second. So with a time step size of 1 millisecond, that means within one heartbeat, we're gonna have 1,000 points of data. Okay. Now there are some phenomena that occur much faster than a heartbeat, right? So for instance, the activity that we're going to do on Thursday, which is a car crash. A car crash happens much quicker than 1 second, and so it occurs in over milliseconds. And so for such a situation like that, you're going to need to use a much smaller time step size in order to accommodate that. Okay. So the only advice that I can give you is to choose your time step size. You want to choose your time step size so that you have enough temporal resolution to fully capture the phenomena that you're interested in. Any questions on the time step size? Okay, so the nice thing about ANSYS is that ANSYS actually chooses the time step size for you. So there's kind of a dynamic algorithm that ANSYS uses to choose that time step size, because it could be something that changes throughout the simulation as well. So that's not something you actually have to worry about on Thursday, unless you want to. You can manually specify the time step size, but a lot of times it's kind of best for ANSYS to kind of determine that for you. Okay. So actually, the one parameter that you do have to input on Thursday is the ending time for the simulation. So the ending time is basically the amount of time that you think that that you need to simulate in order to capture everything that you need to. So when we do our car crash, we're going to set the ending time to be something very small, so just on the order of milliseconds, just because it only takes that long for a car crash to kind of fully play out. Okay. Okay. So the last thing that I want to talk to you about today to get you prepared for Thursday is this idea of the initial conditions of a simulation. So initial conditions is something that's unique to dynamic problems. You could draw the comparison with boundary conditions, and they are kind of similar in some ways. But initial conditions kind of behave a little bit differently. So I want to make sure I go over that. Okay. Now, in dynamic simulations, you are going to be required to do boundary conditions. So this is not a replacement for boundary conditions. Okay. So dynamic simulations, you're going to need both initial conditions and boundary conditions. Okay. Just like you need both the mesh size and the time step size. Okay. So what are initial conditions? Initial conditions basically tell us the state of your entire geometry, of your entire simulation. That includes all of your variables, okay, at the beginning of your simulation. So all the solution variables, that includes things like the deformation or the displacement. So that was our primary solution variable at the, for our static simulation, so we can specify that here as well, okay? But with dynamic simulations, we have new kinematic variables that are available to us, okay? So one variable that we are going to specify as the initial condition for our activity on Thursday is going to be the initial velocity. And so in other words, at the beginning, we're going to say that a certain object or a certain part of our structure is going to be moving at a certain velocity, at a certain speed, okay? In our case, that's going to be the velocity of the car that's going to be ramming straight into kind of a brick wall. Another initial condition that you can specify is acceleration. So what you should notice about all of these quantities here is that these are all what I consider to be kind of the kinematic variables of our solution, okay? And so if you think back to our static simulation, right? Our static simulations, what did we say? So in static simulations, there's always a primary variable that's solved for first. And that is the deformation, okay? In dynamic simulations, our list of primary variables goes up a little bit and to include the velocity and acceleration. And so the thing with dynamic simulations, remember, the way time marching schemes work is that in order for us to solve for the solution at the next time point, the solution at our current time point must be fully specified, okay? And that means all the kinematic variables. So that means the deformation, velocity, and acceleration. Okay. Now, does this mean that you have to specify a deformation, velocity, acceleration for every body in your simulation? No, because if you don't explicitly specify something, then the simulation is going to assume that you have a zero initial condition. Okay. So for instance, the brick wall in our simulation is not going to have an initial velocity. And so the simulation is going to assume that that brick wall is just kind of being stationary. Okay. But just know that all of these have to be fully specified. So, if there's something interesting about your simulation in terms of, an initial velocity or an initial acceleration, you want to make sure that you specify that because that's going to be the starting point in terms of how the rest of your simulation is going to go. Okay. Remember, think of each frame in your dynamic simulation as kind of like a snapshot. And so if you take a snapshot of a dynamic situation, what's happening in that specific snapshot. Okay. All right, any questions on this? Okay, all right, so that's all we got time for today. And so when we come back on Thursday, we're going to be doing our next ANSYS activity. Remember that ANSYS activity is not going to be due until after Thanksgiving. And so, I want you guys to focus mostly on the midterm, but just with the timing of everything, it kind of works out to do this activity now, just so that we can do one more activity after Thanksgiving before we really buckle down for the final. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your day. Thank you for your patience at the beginning of lecture today with the drill. And I will see you all on Thursday.